standing on the deck of a research vessel, watching one of the ocean's most feared predators disappear beneath the waves. The scientists aboard had every reason to believe they were witnessing the beginning of another successful tracking mission. A healthy female great white shark had just been fitted with a scientific tag that would record her movements through the ocean for months. She was nearly 9 feet long, weighed around 500 pounds, and appeared to be in perfect condition. Once released, she swam confidently into the deep blue water, disappearing from sight exactly as the researchers expected. What none of them realized was that this shark would soon become the center of one of the most fascinating mysteries in marine science. For decades, great white sharks have been viewed as the ultimate predators of the sea. They possess extraordinary senses capable of detecting tiny electrical signals from living animals, rows of razor-sharp teeth that are constantly replaced throughout their lives, and explosive speed that allows them to ambush prey with astonishing force. Very few animals willingly challenge an adult great white. Their reputation has made them symbols of power, survival, and dominance in the marine world. Because of that reputation, scientists assumed that once a shark reached adulthood, it occupied one of the highest positions in the ocean's food chain. The research project taking place off the southwestern coast of Australia in 2003 aimed to answer important questions about great white behavior. Marine biologists wanted to understand migration routes, hunting patterns, and habitat use. To accomplish this, they attached electronic archival tags to several sharks. Unlike modern satellite trackers that send information continuously, these devices quietly recorded environmental conditions while remaining attached to the shark. After a predetermined period, the tag would detach, float to the surface, and transmit everything it had recorded. It was an elegant system that allowed scientists to observe animals living naturally without constant human interference. One particular shark quickly became memorable to the crew. Calm yet powerful, she displayed the confidence expected from an experienced hunter. Members of the expedition informally referred to her as Alpha, a nickname that reflected her commanding presence. After completing the tagging process, the researchers watched as Alpha disappeared beneath the waves. There were no signs of injury, illness, or unusual behavior. Everything suggested another routine scientific success. Then, the waiting began. Weeks passed with no indication that anything unusual had happened. Somewhere beneath thousands of square miles of ocean, Alpha continued her journey beyond the reach of boats, divers, and cameras. The only witness accompanying her was the small electronic recorder attached to her body. Months later, the tag detached exactly as designed. But Alpha never returned. When the device was recovered, researchers expected to see a normal record of a great white's movements. Instead, the data raised questions that no one in the room could answer. The first anomaly involved depth. For much of the deployment, Alpha behaved exactly as expected. She moved through coastal waters, making dives typical of adult great whites. Then, without warning, the recorded depth changed dramatically. The tag documented an extraordinarily rapid descent to nearly 1,900 feet beneath the surface. Although great white sharks are capable of making occasional deep dives, such an abrupt plunge was highly unusual. It did not resemble a normal hunting dive or a gradual exploration of deeper water. Instead, it appeared as though the shark had been taken downward with remarkable speed. That alone would have attracted scientific attention. Then researchers noticed the second anomaly. At a depth approaching 1,900 feet, seawater temperatures are expected to be extremely cold, roughly 46 degrees Fahrenheit, depending on local conditions. Instead, the tag recorded something astonishing. The temperature surrounding the device suddenly increased to approximately 78 degrees Fahrenheit. Even more remarkable, it remained stable. The equipment had not briefly warmed before cooling again. The temperature stayed elevated for an extended period. Scientists immediately began questioning whether the tag had malfunctioned. Electronic devices occasionally fail. Sensors can produce incorrect readings. Batteries weaken. Saltwater can damage internal components. Every possibility had to be considered before reaching any extraordinary conclusion. Yet repeated examination revealed no obvious evidence of equipment failure. The temperature sensor had functioned normally before the event. Other recorded measurements appeared internally consistent. The data followed a logical sequence rather than random fluctuations expected from a damaged instrument. If the readings were accurate, only one explanation seemed capable of producing such conditions. The tag was no longer surrounded by seawater. It was inside a living animal. That realization transformed a curious scientific observation into a genuine mystery. What kind of creature could swallow a great white shark? At first glance, the answer seemed obvious. Orcas. Also known as killer whales, orcas are among the few predators known to attack great white sharks. Modern observations from South Africa and other regions have shown that some orca populations have developed specialized hunting techniques targeting sharks, often removing the nutrient-rich liver while leaving the rest of the carcass behind. Their intelligence, strength, and cooperative hunting behavior make them formidable predators capable of defeating animals that would terrify almost anything else in the ocean. Because orcas are warm-blooded mammals, the elevated temperature appeared consistent with being inside one. But another problem emerged: the recorded dive. Orcas certainly dive beneath the surface, yet the specific pattern recorded by Alpha's tag did not perfectly match known orca hunting behavior. Researchers found themselves comparing every detail against what was known about marine mammals, searching for a convincing fit. Some scientists suggested sperm whales. These enormous mammals routinely dive thousands of feet in pursuit of squid and spend long periods in deep water. Their ability to reach extreme depths made them an intriguing candidate. However, sperm whales primarily consume squid and fish rather than large sharks. Their internal body temperature is also considerably warmer than the value recorded by the tag, making the evidence less convincing. Other possibilities quickly faded. Could a giant tiger shark have attacked Alpha? Not likely. Even the largest tiger sharks are generally not large enough to swallow an adult great white whale. Could a colossal squid somehow have dragged the shark into darkness? That theory collapsed immediately because squid are cold-blooded animals. They could never produce the stable warm temperature observed by the recorder. Every possible suspect explained one clue while contradicting another. Some could reach the required depth, but possessed the wrong internal temperature. Others had suitable body temperatures, but rarely hunted in the necessary environment. The mystery refused to disappear as researchers continued analyzing the evidence. They noticed something about great white sharks that suddenly became incredibly important. Unlike most fish, great whites possess a remarkable adaptation known as regional endothermy. Through specialized blood vessels, they retain heat generated by powerful swimming muscles, allowing certain internal organs to remain significantly warmer than the surrounding water. This adaptation enables great whites to hunt effectively in colder environments, where many other fish would become sluggish. That single biological fact changed everything. If an exceptionally large great white possessed an even warmer internal core than average, if it was capable of diving much deeper than previously believed, if cannibalism occasionally occurred among sharks, then perhaps the impossible explanation was not impossible at all. Perhaps the predator wasn't a whale. Perhaps it wasn't an unknown monster hidden in the abyss. Perhaps the hunter belonged to the very same species as the victim. And if that was true, then somewhere in the vast waters off Australia, there had once been a great white shark so enormous that another adult great white represented nothing more than a meal. By the time researchers finished reviewing Alpha's tracking data, one fact had become impossible to ignore. The shark had almost certainly died, but understanding how she died proved far more difficult than anyone expected. The electronic tag had recorded an event unlike anything scientists had previously documented in a mature great white shark. Every answer created another question, and every possible predator seemed to explain only part of the mystery. Marine biologists approached the problem the same way detectives investigate a crime scene. They began by identifying every known ocean predator capable of attacking a large great white shark. Each candidate would be measured against the evidence recorded by the tag. If even one major piece of evidence failed to fit, that suspect would have to be eliminated. The first and most obvious suspect remained the orca, also known as the killer whale. Orcas are among the ocean's most intelligent predators. They hunt cooperatively, communicate through complex vocalizations, and have developed specialized hunting techniques unique to different populations around the world. In South Africa, scientists have documented orcas attacking great white sharks with astonishing precision. Instead of eating the entire shark, they often flip it upside down, inducing a state called tonic immobility before removing the nutrient-rich liver. These attacks are so effective that great white sharks have been observed abandoning entire feeding grounds after orcas appear. At first glance, the evidence seemed promising. Orcas are warm-blooded mammals, which could explain the sudden increase in temperature recorded by Alpha's tag. They are certainly strong enough to kill a shark of her size. But one crucial detail refused to fit: the depth. Although orcas are capable divers, they generally hunt within the upper layers of the ocean. Even their deepest recorded dives fall well short of the prolonged descent shown by Alpha's tracking device. There was no evidence suggesting an orca had dragged a freshly killed shark nearly 1,900 feet into cold, dark water before remaining there. The theory explained the temperature. It did not explain the dive. Scientists reluctantly moved on. Their next suspect was the sperm whale. Unlike orcas, sperm whales routinely descend thousands of feet beneath the surface in pursuit of giant squid. Their massive bodies are perfectly adapted for deep diving. Some individuals remain underwater for more than an hour before returning to breathe. On depth alone, sperm whales appeared to be an excellent candidate. Yet once again, another problem emerged. Sperm whales primarily hunt squid, not large sharks. More importantly, their internal body temperature is considerably warmer than the approximately 78 degrees Fahrenheit recorded by Alpha's tag. If the device had entered the stomach of a sperm whale, researchers expected an even higher temperature. Once again, the evidence refused to cooperate. Next came the large predatory sharks. Tiger sharks are famous for eating almost anything they encounter. Sea turtles, seabirds, dolphins, rays, and even discarded human objects have all been found inside tiger shark stomachs. Their reputation as opportunistic hunters made them worthy of consideration. But size quickly eliminated them. Even exceptionally large tiger sharks simply are not big enough to swallow a fully grown 9-foot great white whale. Their jaws and throat structure make such a feat extremely unlikely. Other shark species faced the same problem. They were dangerous. They were aggressive. But they weren't large enough. One by one, the list of suspects grew shorter. Some researchers briefly considered more unusual explanations. Could a giant squid somehow have captured the shark? The answer was almost certainly no. Although giant and colossal squid possess enormous tentacles armed with powerful suckers, they are cold-blooded animals. Their body temperature closely matches the surrounding seawater. They could never account for the stable warm temperature recorded by Alpha's tag. That possibility disappeared almost as quickly as it appeared. After months of discussion, scientists found themselves facing an uncomfortable reality. No known predator perfectly matched every piece of evidence. Then someone asked a question that initially seemed almost absurd. What if the predator wasn't a different species? What if it was another great white shark? At first, the suggestion sounded unbelievable. How could one great white possibly swallow another? The answer lay in a remarkable biological adaptation shared by only a handful of shark species. Unlike most fish, great whites belong to a group known as lamnid sharks. This family includes the shortfin mako and salmon shark, species capable of retaining heat generated by their swimming muscles. Through a network of specialized blood vessels, much of that heat is recycled back into the body instead of being lost to the surrounding water. Scientists call this adaptation regional endothermy. Instead of having body temperatures identical to the ocean around them, great whites maintain warmer muscles, brains, eyes, and digestive organs. This allows them to hunt efficiently in colder waters, where many other fish become slow and inactive. The larger the shark, the greater its ability to retain heat. That simple fact suddenly transformed the mystery. If an exceptionally large great white had swallowed Alpha, the tag could have experienced exactly the temperature researchers observed. Even more surprising, modern tracking studies have shown that great whites are capable of diving far deeper than previously believed. Although they spend much of their lives near the surface, some individuals regularly descend well beyond 1,000 feet during migrations across the open ocean. Suddenly, the depth no longer seemed impossible. The temperature no longer seemed impossible. Both clues pointed toward the same answer. But one enormous question remained. How large would a great white need to be to swallow another shark measuring nearly 9 feet in length? Researchers turned to biomechanics, jaw measurements, and feeding behavior. Their estimates suggested that the predator would likely need to measure somewhere around 16 feet or more, weighing well over 2 tons. Such sharks are rare, but they are verified. Individuals exceeding 18 feet have been documented, and some estimates suggest that exceptionally old females may grow even larger. That realization changed the entire investigation. Instead of searching for an unknown monster hiding in the deep ocean, scientists were now looking at an extraordinary, but entirely real, member of a species they had studied for decades. The evidence suggested that Alpha had not been attacked by something outside the known food chain. She may have been killed by a giant version of the very predator people believed sat at the top of that food chain. If true, the implications stretched far beyond one unfortunate shark. It suggested that the ocean's hierarchy was more complex than scientists had imagined. Even apex predators could become prey under the right circumstances. And if great whites sometimes hunted one another, then many long-held assumptions about shark ecology would need to be reconsidered. The mystery was no longer simply about Alpha. It had become a question about the hidden lives of the largest sharks on Earth. By now, the evidence had narrowed the field dramatically. The strange temperature readings, the rapid descent into deep water, and the biological characteristics of great white sharks all pointed toward one conclusion that once seemed impossible. A much larger great white shark was the most likely predator. It wasn't the dramatic answer many people expected. There was no prehistoric sea monster emerging from the darkness, and no unknown giant lurking beneath the waves. Instead, the most unsettling possibility was also the most scientifically grounded. The ocean's most famous predator may occasionally become prey to an even larger member of its own species. That realization forced researchers to revisit decades of observations they had once considered isolated incidents. For years, marine biologists had documented adult great white sharks bearing enormous bite scars. Some wounds were so large that only another great white could have made them. In many cases, the shark survived, carrying these scars for the rest of their lives. Until Alpha's disappearance, many scientists interpreted these injuries as territorial disputes or aggressive encounters over food. But what if some of those attacks were not fights? What if they were failed hunting attempts? The idea suddenly seemed much more plausible. Cannibalism is not unusual in the animal kingdom. Crocodiles, lions, polar bears, wolves, and numerous fish species have all been observed killing members of their own species under certain conditions. Sharks are no exception. In fact, cannibalism begins before many sharks are even born. Inside the womb, embryos of several shark species compete for survival. In species such as the sand tiger shark, the largest embryo consumes its smaller siblings before birth, a phenomenon known as intrauterine cannibalism. Although great white sharks reproduce differently, competition among shark offspring demonstrates that cannibalistic behavior has long existed within the shark family. Adult sharks also display opportunistic feeding habits. If an injured, weakened, or smaller shark becomes available, a much larger individual may not ignore such an easy meal. From an evolutionary perspective, the behavior makes perfect sense. A large shark represents an enormous package of calories, rich in fats and proteins, requiring relatively little energy to consume once it has been overpowered. For an apex predator, survival is about efficiency. The ocean does not reward hesitation. Researchers also began comparing Alpha's case with similar tracking studies involving other shark species. In several instances, electronic tags recorded sudden increases in temperature followed by unusual movement patterns, suggesting that the tagged animals had entered the digestive systems of larger predators. While not identical to Alpha's case, these events reinforced an important lesson. Modern tracking technology was revealing interactions that humans had never directly witnessed. For centuries, scientists relied primarily on observations made near coastlines, from fishing boats, or by divers working in relatively shallow water. But the open ocean is vast beyond imagination. More than 70% of Earth's surface is covered by water, and the overwhelming majority of that environment remains difficult to observe continuously. Much of what happens hundreds or thousands of feet below the surface occurs without a single human witness. Electronic tags have changed that. Every year, new generations of satellite transmitters, depth recorders, accelerometers, and environmental sensors allow researchers to follow marine animals farther than ever before. Instead of depending solely on occasional sightings, scientists can now reconstruct entire journeys across thousands of miles of open ocean. Sometimes those journeys reveal expected behaviors. Other times they reveal something no one predicted. Alpha's disappearance became one of those moments. Although the evidence strongly suggested predation by an exceptionally large great white shark, researchers have remained careful in how they present their conclusions. Science rarely deals in absolute certainty, especially when direct observation is impossible. Instead, scientists evaluate competing explanations and determine which best fits the available evidence. In Alpha's case, the giant great white hypothesis explains the recorded depth, the elevated internal temperature, the biological characteristics of the predator, and the known, though rarely observed, occurrence of cannibalism among sharks. That does not mean every question has been answered. Far from it. Where did the attack happen? Was Alpha ambushed from below, the way great whites typically hunt seals? Was the larger shark defending territory, competing over food? Or was this simply an opportunistic encounter between two predators whose paths crossed in the open ocean? No one knows. The tracking device recorded the aftermath, not the attack itself. Perhaps the most fascinating aspect of the entire mystery is what it reveals about scientific discovery. Many people assume that the ocean has already been fully explored, that every major predator has been cataloged, every important behavior documented, and every mystery solved. Reality is very different. Scientists estimate that a significant portion of the deep ocean remains poorly explored. New marine species continue to be discovered every year, including fish, corals, crustaceans, and even large deep-sea animals. Advanced underwater vehicles regularly capture footage of creatures never before seen alive. If new species are still being discovered in the 21st century, it should not surprise us that familiar species continue to reveal unfamiliar behaviors. Great white sharks have been studied for decades. Yet Alpha's case demonstrated that even one of Earth's most recognizable predators can still surprise science. It also reminds us of an important truth. Nature does not organize itself according to human expectations. We often imagine food chains as simple pyramids with one unquestioned ruler at the top. But ecosystems are far more dynamic. Age, size, opportunity, environment, and behavior all influence who survives and who becomes prey. Even the hunter may someday become the hunted. Today, researchers continue tagging sharks around the world. Every transmitter attached to an animal represents another opportunity to learn something completely unexpected. Somewhere beneath the waves, another great white is swimming through water that no human has ever seen. Another electronic tag is quietly recording temperatures, depths, and movements that could one day reshape our understanding of marine life. Perhaps the next great discovery is happening right now. Perhaps another mystery is already stored inside a tiny recorder waiting to wash ashore. Alpha Story is more than the tale of a missing shark. It is a reminder that the ocean remains one of the last truly wild frontiers on Earth. Every expedition uncovers new questions. Every answer reveals another layer of complexity. And every scientific breakthrough reminds us how much remains hidden beneath the surface. The greatest surprise was never that a great white shark disappeared. The real surprise was discovering that even an apex predator can have an apex predator of its own. And somewhere in the immense blue wilderness, an exceptionally large great white may still be patrolling the depths, unseen, untracked, and completely unaware that its existence has transformed one of marine biology's most remarkable mysteries. If one scientific tag could reveal a story like this, imagine what the next one might uncover. Because the ocean has a habit of reminding us that no matter how much we think we know, there is always something deeper waiting in the darkness.